Okay, so we're just going to go over some of the basics of telescopes and mounts, just so you have a rough idea of some of the differences. You'll understand a little bit of what you're reading about if you're looking to buy one, or maybe if you just got one, maybe you understand a little bit more about what the components are, and some common terminology. So let's see. Oh, yeah, first that's not going to work here. Okay. First we're going to start with the types of telescopes and the common components of them. So all the telescopes are doing the same thing, right? They're taking a wide opening of light and focusing it down to a small point of light that's at the same focal plane, so your eye can see something brighter and larger than what it sees without any assistance. The lenses or mirrors are what are doing the majority of that focusing. You either have a lens system, a mirror system, or a combination of both, and we'll talk about those in a moment, what they're called and how they differ. The eyepiece is going to be the last part of the back end of the telescope. That's what, well, usually the back end, sometimes toward the front, that you're actually looking through. That's taking the now focused condensed light and kind of magnifying it for your own eye. You have the focuser, which is going to refine the position of that eyepiece to match where that focal plane is that's being projected by those lenses or mirrors. Sometimes the focuser is moving the eyepiece, and sometimes it's actually moving a part of the optical train, like the actual mirror. In either of those cases, that's either moving the lens, either moving the eyepiece into the focal point or moving the focal towards the eyepiece. You also have a finder scope. That's basically just to assist you in targeting your primary scope. So the finder scope is going to be attached to the body of your regular scope. It's going to either have lesser magnification or maybe even no magnification, depending on the type of finder scope that you have. And the whole point of that is it'll be aligned with your primary scope. So when you look through your finder scope and point that and center something in the finder scope, you can then move to the higher magnification of the primary scope, and it'll be in the center there also. You have the optical tube assembly. That's basically the structure around the scope. So whether you've got lenses or you've got mirrors, you've got a tube or some kind of structure that's holding those mirrors and lenses in place. That's the optical tube assembly, kind of holding it all together. So the other part's the diagonal, the mount and the tripod I didn't touch on here. The diagonal is basically on the end of some scopes. If you've got a scope like a refractor where it's just a straight through light beam, if you were to just look at the eyepiece behind it and you're looking at something very high up in the sky, you're gonna have to like kneel down, get really beneath it. So you might have a diagonal that's basically just a mirror that's reflecting that light, so that now you're looking at a 45-degree angle to the direction of the scope. And that way it's a lot more comfortable to look through, to actually see what you're looking at. Not all scopes utilize a 90-degree. We'll look over some of those. Some do. It just depends on the design where that light's exiting the telescope. Then you got mount and tripod, not to be confused with each other. The mount holds the telescope onto the top of the tripod. So there's different types of mounts that you can have on top of your tripod. The tripod also can be replaced with a pier if you're putting in like a permanent installation. That way, if it's not portable, then you can just literally bury a pier into your ground below the permafrost, and it can be, permanently mounted right there. But the tripod or the pier, that's just holding up the mount, which is holding up the telescope. So we've got aperture, objective lens, and focal length. So the aperture is the diameter of the opening of the front of the scope. It's basically how much light your scope is able to gather. And the more light you're gathering, the dimmer of an object you can pick up in that telescope, and also the higher useful magnification you can get out of it. There's a maximum amount of magnification based on the aperture, where at a certain point you can keep magnifying it, but you're just going to make a blurry image bigger. You're not actually going to be able to get additional resolution out of that. The objective lens is that front lens on your refractor or on your telescope. Usually it's equal to the diameter of the aperture. It's basically just the first lens that's dealing with the light. You've got a focal length, which is the distance between that first lens or the mirror that you're focusing the light from and where your camera sensor or where your eyepiece is going to catch that light. It relates to how much magnification you can get out of a telescope and what's called an F ratio, which I'll talk about in a second. So just to make that a little more clear, the longer your focal length, the more magnification you can get. But it's also a relationship magnification is with your eyepiece, which we mentioned here. So the focal length of your telescope divided by the focal length of your eyepiece is going to be the magnification. So if you have, a 1,000 millimeter focal length telescope and you're putting into it a 10 millimeter eyepiece, you're getting 100x magnification out of that. But if you put that same eyepiece at 10 millimeters into a 400 millimeter telescope, you're only getting a 40x magnification. It's to divide the focal length that's shown on the eyepiece into the focal length of the telescope. And by the way, I will put these slides online and we'll have a recording of this as well. So I see some furious writing, which is fine. But if you miss anything, don't worry about it. You'll be able to look at it again. Just trying to not, trying to get to the meat of the presentation with helping people out directly. So the F ratio that I mentioned before is actually the focal length divided by the aperture. And that relates to basically how fast your scope is focusing the light and how magnified it can possibly be. The higher focal ratio is going to give you a narrower field of view, but you can get finer details out of that. A lower focal ratio, you're going to get a wider field of view, but you're going to collect the light faster and get less, the details aren't going to be quite as fine. So it's a little bit weird to kind of imagine what that means, but just in case you come across that, you'll see F ratios mentioned a lot. And that's kind of what that means. It's basically how fast is it focusing the light. It's a little more important with cameras than it is with visual, but you'll still see that around a lot. And then you've got a lot of times in the specs of like a telescope, if you're on the Celestron site or whatever, you'll see like maximum magnification and like maximum useful magnification. A lot of people wonder what's the difference. Basically, the mathematical maximum magnification that you can have is assuming you have like perfect conditions. And we're in the Northeast, we never have perfect conditions. You basically have to go to like the Atacama Desert or middle of the ocean or something like that to get to really perfect skies where maybe you could really push the telescope to that level. So useful magnification is a little more of a better metric for us to see how much could we really push that scope in a more average environment. And because there's some marketing at play, a lot of times even the useful magnification is a little on the optimistic side for a Northeast type of environment. But so if you see those two, that's why there's two different numbers and sort of what they represent. So a lot of text on this one. Again, you'll be able to review this, but I'm just going to speak to it. So refractors are using all lenses. The lenses tend to be heavier and more expensive than mirrors. But as we noted before, the lenses are cemented in place. So there's no, they're low maintenance. They're permanently aligned unless you drop them or damage them. You'll see sometimes reference to the gaps between the lenses as either air gapped or oil gapped. Doesn't really matter which one they are. That's just a matter of what's in between the lenses. And the oil actually has a refractive property to it, and air does. And so it just kind of changes the way it's designed, but it doesn't really matter which one they are. Mostly you'll just see air gapped. That's not good or bad. It's just a difference. The bigger thing to pay attention to is you'll have either achromatic or apochromatic refractors. The cheapest version are achromatic or achromatic. Basically, that's when you have a single lens that's focusing at the front all the way down the length of the tube to your eyepiece pretty much directly. Because of the nature, if you remember physics, or if you haven't taken physics yet, wavelengths of light refract at different angles when they go through a lens. And so to get the colors that are closer to the purple end of the spectrum to line up with the colors that are in the red end of the spectrum, they're bending differently. And so if you just have a single lens, you can't bend all of them perfectly evenly without having additional lenses to add corrections in there. So a single lens system, an achromatic system like this, tend to suffer from what they call chromatic aberration. And also because of the fact that you're bending everything at once, but can't bend it all perfectly to the same point, you also get a spherical aberration, which is basically, you might have focus in the center of your field of view, but it might be blurry on the outside. That doesn't necessarily matter depending on what you're looking to do, right, and how much you're willing to pay to correct stuff like that. A lot of times the targets we're looking at might only be in the center of your field of view. It's not the full field of view, so then who cares, right? Or if it's looking at a deep sky object that you're not going to be able to resolve the color anyways, then chromatic aberration is less of an impact for you. Or if you're doing photography, narrowband, you're only looking at maybe a specific wavelength, then achromatic can actually be a cheap way to get a decent scope out of it. But usually the sweet spot for most visual tends to be like a doublet apochromatic. They're a little bit more expensive than an achromatic because they have one extra lens in them, and it resolves the majority of the chromatic aberration that we just talked about. And the way the chromatic aberration looks, if you're looking at like a bright object like the moon or Jupiter, you end up seeing like a tinge of color on either side of that object. It might be kind of a bluish hue on one side and a yellowish or reddish hue on the other side. because the light of that image is actually not coming back perfectly to the same spot. So a doublet adds one extra lens to try and correct the majority of that. Once you get to the triplet and the quad, they're each adding additional lenses also, one additional one each, as the name suggests. The triplet further corrects that color aberration, and then the quad actually flattens out the field to get rid of the spherical aberration. Those two are usually not, for the visual astronomer and definitely for the starting astronomer, not necessarily worth the upgrade. They're a lot extra money. They're mostly useful in photography, where you've got long exposures and that stuff really stands out. With your eye being less sensitive than the camera, it's not usually worth that kind of an upgrade. But depends how much money you have. So here's the general idea of how a refractor works. You've got the glass. This is your one lens in the front. This would be like an achromatic design. So it's just going through one glass that redirects that light towards your eyepiece back here. If you had a doublet, it would have one extra piece in there that further corrects that to get those a little bit closer together. And again, triplet and etc. But very basic concept, one lens in the front, eyepiece in the back, super simple design. If you see baffles, we have talked about those. That's basically the path that this light is being bent at is mathematically calculated not to extend wider than this gap here and wider than this gap here. So there's a ring inside the scope at a couple different points, just to block any extra light that might be coming down where it shouldn't be, where we know that the light that you care about shouldn't be, to keep it from bouncing around inside your tube and causing more interference further down the scope. So reflectors, they use only mirrors. Everyone used only lenses. This uses only mirrors. Newtonians are this kind of the de facto standard for reflector, developed by Newton himself. You end up with a large primary mirror at the back end, and this is the front end here. The back end here, you get a big primary mirror that reflects light to the front off of this little secondary mirror that you can see poking out in the front. And that secondary mirror is actually at an angle and it's oblong, and it takes that light and reflects it 45 degrees out the front end of the scope here. So you actually look through the front of the scope here because the light's going all the way to the back, off of this secondary to the front, and then through this focuser to the eyepiece here. So these are mirrors, like I said, are cheaper and lighter than the lenses. So these tend to be cheaper to build. They tend to be a little bit lightweight relative to the size, if you were to get equal sizes of a refractor. But they're still plenty good, and they're very, very common. The one thing to note, if you're going to get one of these, if you ever see one that says it's a spherical mirror system, just avoid those. They're known really difficult to collimate and not usually very good images. You're going to primarily see and should look for parabolic mirror systems. That avoids the issues entirely that the spherical ones run into. There's different names for those and whatever, but if you look around online, you'll see that as a common thing to pay attention to. So with this one, you can see here, this rotary here actually pushes the eyepiece in and out. So the eyepiece is moving towards the focal point or away from the focal point. And you can tell because it's already the light's already coming out the side of the tube here, you don't need any kind of 90-degree diagonal, like I mentioned before. Whereas the refractor, when you're coming off the back of the refractor, you could possibly just extend this past here and have an eyepiece going straight through it, kind of like the design we see here, except that gets really uncomfortable when you're trying to look at something high in the sky, right? So you put this 90-degree mirror instead, and now you can rotate that mirror any direction you want, left or right, but then at least you're not trying to get behind the telescope. So going back to the reflectors. So these ones do need a slight collimation before each use. If you're particularly, the more you move them around, nothing major, just takes a minute or two just to dial it back into play to make sure the mirrors are perfectly facing each other the way they need to be. And there are a couple other refractor designs. Usually most of them are hybrid. Not really worth getting into, not as common, but they do exist. But the general concept is you've got a vane, like a spider vane system here, just little metal armatures that hold the secondary mirror. The light goes right past that secondary mirror, reflects off the primary in the back, and then hits the angle of the secondary to come out the side into your eyepiece. So now there's also Dobsonians. It's even this slide's a little bit wrong because I wrote it and then I realized I wrote it a little bit wrong. But basically, the Dobsonians do exist as a type of telescope, but the way that term is used these days, majoritively, really just refers to a Newtonian telescope on a Dobsonian style mount. So the mount is unique. If you look here, this isn't a tripod. It's a structure basically like a lazy Susan with armatures on it, and the arms hold up the telescope, and then it pivots up and down and left and right on that lazy Susan. There is actually such a thing as a Dobsonian telescope, but its whole design was about making the mirrors thinner and lighter and cheaper at larger apertures, where you might have a Newtonian scope that has maybe a, half an inch thick glass in the back. A Dobsonian scope would use a 1/4 inch thick. It was about half of the thickness, but then it had other things in place, straps and things to support that mirror, because as the mirrors get big, they need some extra structure to not warp. So you won't find those very often these days. So mostly if you see something referred to as a Dobsonian anymore, it really means a Newtonian telescope on a Dobsonian style mount. And we'll talk about the mount specifically in a little bit. So catadioptrics, these are a blend of mirrors and lenses together. The most popular is the Schmidt-Cassegrain. It's got flexible focal lengths, especially once you get to the 8-inch and higher. You can actually put on different accessories that will change the focal length just with that accessory without having to swap out a completely different telescope. And they are compact because of the way they're designed. The secondary mirror that's in the front blocks about 30% of the aperture, but you still get, so if this is like a 6-inch aperture, you're blocking 20% of that, about 2 inches or so of that light from getting in there. So it's not equivalent to, it would be equivalent to like a, what is, I think, a 3 or 4-inch refractor or something like that in terms of the amount of light you're actually collecting, even though it looks bigger. There's a corrector plate in front that actually holds the secondary mirror in place instead of those spider vanes that we saw in the Newtonian. And the light goes through, bounces off the back, just like a Newtonian, and off the secondary, just like the Newtonian. But instead of it being at a 45-degree angle to come out the side of the front, you'll see it actually comes straight out the back and back end here, and you end up using a diagonal to be able to see that, so you're not getting behind the scope. The way that works is there is a primary mirror back there, but it's donut shaped. There's a big hole in the center, and so the light is coming, basically all the light that's being blocked by this secondary here, it doesn't bother with the mirror in the center there, reflects that light off of the secondary and then continues to focus that through the donut hole in the center of the primary and out the back. So it's kind of a compressed design. I didn't talk about this before, but when you put a new telescope out, you want to let it acclimate to the temperature in order to let the optics kind of shift and adjust and whatever, because glass condenses and everything else when it gets cold. So you want it to or contracts, I should say, not condenses. So you want it to settle basically and meet the outside temperature before you really start using it for the best view. Generally, you need at least 30 minutes for that to happen, but the bigger the scope and the bigger the glass, the longer that can take. When you have a scope like this that's closed, which is similar to a refractor being closed, there's no air getting into the actual tube. And so it actually takes a little bit longer to let these cool down. Some you'll find have little vents on the back to try and help get a little bit of air in there, but you do need to give them probably 45 minutes instead of a half hour. Oops. So the other type of catadioptric that's common is a MHAA Cassegrain, which was mentioned earlier a little bit. It's very similar to the SCT in look, but it's not necessarily, in my opinion, ideal for a starter. They're much more expensive. One of the main benefits of them is they have a smaller secondary, so they block less of the aperture, about half as much aperture as the SCT secondary does. But they tend to have a narrow field of view as a result of this design. So you get a higher magnification out of a smaller scope. And they tend to be significantly more expensive. And I haven't used them personally, but I've heard that they're a little more difficult to collimate as well than an SCT and others. So just to kind of play on that point, I don't know if I can move this. So the top image is a Schmidt-Cassegrain, the bottom is a MHAA Cassegrain. The primary difference is really this front lens here and the shape of it in terms of the way the design looks. But otherwise, it's the same kind of concept where your light's coming in, bouncing off a donut-shaped primary mirror to the secondary mirror on the back of that corrector plate in the front, and then through the donut hole to the back of the eyepieces. So The last one here is called the astrograph, or the full name being a Rao Ackerman Schmidt astrograph. Very similar design to the SCT, except instead of bouncing the light back through the back end, it stops right here in the front. And these are, you can tell that you can't use these for visual, because you'd be putting your face right in front of the scope. You'd be blocking all the light. So there's no place to put an eyepiece on these. They're called astrographs because they're entirely designed for astrophotography. So it's entirely meant for a camera to be strapped to the front of this thing. There's nowhere on the back here you can see, nothing that lets the light out the backside. They tend to be very fast, but not good for, not even usable for visual astronomy, and not something to start with as a starter. And they're kind of expensive too. So you got binoculars. So these are actually a really good way to start for a lot of people, especially if you're brand new to astronomy, and you're not sure, how into it are you. It's essentially two small refractors strapped together. They tend to refer to them by their numbers. You'll see a 10 by 50. It's not a multiplication thing. It's just 10x is the magnification. That's the first number. And the second number is the aperture size, or the size of those lenses on the front of the binocular. They're a good way to start because they're very compact, they're low maintenance, they're very portable and affordable. And you can see quite a bit even with binoculars. And I actually have a book up here when we're done with targets specifically for binoculars that you can check out if you want. And I brought binoculars over there as well. These are the same ones that are in the picture here. So don't use what you find online like spotting scopes and daytime type scopes if you can avoid them. If you have them, it's not a horrible way to start with what you got. But you can find astro-specific binoculars that are fully coated. They're meant for allowing more transmission of light through the lenses because you're looking at dimmer objects, whereas daytime stuff doesn't have to be as picky because you're getting tons of light during the day. And the coatings and stuff will make sure you get less reflections and other aberrations like that. Also, you can find sometimes the pro version of binoculars, like the one that's over there. They tend to be waterproof. They'll have they'll purge that intersection between the lenses with nitrogen to make sure that you don't get humidity building up when you go, because they know you're going to be outside often in the cold air, and you don't want the inside of your lenses fogging up or moisture building up in there. You get mildew, that kind of stuff. So if you can afford them, they're a little bit extra, but you can get a pro version often that'll protect against that. And then in terms of max power on those, if you go over 10x, it can be hard to hold them steady. So if you're planning on going over 10x, you're going to want to invest in a tripod at least, and possibly a parallelogram, which is what we'll talk about a little bit too. That's a type of mount specific for binoculars. Because when you're trying to look at something neat, if it's bouncing all over the place, it's really hard for your eye to counteract that movement and really get the best view of that target. So in kind of a general suggestion, for planetary, moon, double stars, you can consider a 70 to 90 millimeter or higher refractor. If you kind of just want sort of a jack of all trades, the parabolic Newtonians, 130 millimeters or higher would be a good suggestion, including Dobsonians. Catadioptrics, I would sort of steer brand new people away from a little bit, just because they are a little bit more money, unless you really are ready to just know that there's going to be a steeper learning curve to that, but you want to stay in it for the long haul. Because they are flexible, they can be a decent way to start, but you just need to know already that you're invested in that. But the biggest suggestion is always, from anybody you talk to, going to be pick the scope you're willing to carry in and out of your house. Some people get a little excited. They buy a 14-inch scope, something that weighs a couple hundred pounds, and it makes a great coat rack because they never want to carry that in and out of their house because it's just such a bear. But if you've got a 6-inch and you're going to use it every day, that's going to be worth more to you than having some giant 14-inch beast. Not to mention, if you're starting, the bigger the scope like that, it's actually a tougher learning curve because the magnification is so high. There's a lot more that can be off and be hard to fix without knowing what you're doing. So a lot of those images I took off of this website. Again, you'll be able to get this later from the replay, and I'll put it in the comments. But I just mentioned it because he did have a lot of good info and details in there about the different designs and expectations and the chromatic aberration. He actually kind of shows an example of what that means, those different types of refractors. So for more follow-up, you can use that. So I'll go into mounts real quick, hopefully quick. Like I said, the mount is on top of your tripod or on top of your pier. It's what is holding on to your telescope and allowing the telescope to actually move. So there's two different ways to move your mount, or two different coordinates that you're moving your mount within. The simplest one is what they call alt-azimuth. So it's up, down, left, right, relative to your horizon. So you say, okay, I want to go to Jupiter. It's over there. You move your telescope up. You move it over to Jupiter. Right? Real simple from a mental perspective to figure out how do I move the scope to that thing. There's different types of mounts that have that type of movement, and they've got their pros and cons. The one on the left here is kind of a standard alt-az mount, but what it has, the reason it's telescope specific, or that you know it is that it has these kind of fine-tuned knobs on it. Right? So you can move the scope roughly by hand to get it kind of close, and use your finder scope to kind of dial it in a little bit closer. And then you use these little knobs on the bottom on the side here that drive these little screws to do the minute movements to really dial it into the center of your field of view. Because a lot of times just moving it by hand is too much movement since you're focusing on something so far away. So, and often so small. Now you can also find these pan tilt ones, which are like a camcorder style mount head. Those usually have, you grab this handle, you twist it to unlock it a little bit. That gives you the free motion to move it around and point it where you want it, and then you twist it to lock it. The problem is often that when you, particularly the cheaper ones, when you lock it, that nudges it a little bit. So, okay, it's in the center of your field of view, and then you lock it, and all of a sudden, there goes your, it's out of your field of view again. So it can be maddening for something that's the higher magnification you have, to be moving out of your way when you think you have it right, but you got to figure out how to counteract that locking nudge. So I don't generally recommend those too often. The fork mount on the right side here, this tends to be only really seen with a motorized mount, computerized mount. There's going to be motors in there that'll actually rotate the base and tilt it up and down, but it's still alt-azimuth in terms of its movement. They'll have a computer you can see on the side. There's a little hand controller on the side. You can either drive it manually with the buttons on the controller, or you can tell it to go to something if you set up your telescope ahead of time to be orientated with where it's pointing at the sky. So Dobsonians and parallelograms, again, these are still alt-azimuth mount style in terms of their coordinates, how they move. Again, this is that Newtonian scope. Here's that Dobsonian mount. It's just going to pivot up and down, and it's going to rotate on the Lazy Susan on the bottom to move left and right. This is a Dobsonian mount as well, slightly different style, but it's the same concept. It's just sitting on top of a little pad that has a little bit of friction. This one over here, the problem with these ones in the middle, or one of the difficulties they have, is as you go lower on the horizon, you've got all this weight on the front end, and you're getting less and less weight on this back end, so you're losing the amount of friction you have. And all of a sudden, maybe there's spots that are low enough that you can't actually let the telescope rest there because it's just going to continue falling. And whereas, so you can't really, it's difficult to add friction, without adding like extra weights in the back here to try and counteract that. This style of Dob mount, you can actually basically squeeze the tube a little bit. There's screws on each side that are holding that tube in, that telescope in. And usually one of them has a little like a friction washer. And so you can just tighten it just a little bit more if you're going down towards the horizon to make sure that it doesn't continue falling when you let go of it. So I tend to prefer this style, but these are a little bit more compact. They can break down. And I'll also mention here, this Dobsonian, you can see you don't necessarily need a metal tube to make a telescope. This is a structure that holds the secondary optics out here, but it's performing the same task as having a tube holding secondary optics out here. The only difference would be this is going to let in more light from the side. So if you've got these houses in the background, you would want to put a shroud over this to kind of keep that outside light from getting in from the side angles. And then lastly, you've got the parallelogram, which is over here in the room. Like I said, if you've got a binocular on the center of your tripod and you're trying to look up, your chin's getting closer and closer to that tripod. There's literally spots in the sky you won't be able to get to that are closer to your zenith straight up. So with the parallelogram, it pushes that, it balances the center of weight still on the center of the tripod by using a counterweight over here. And usually when you, like that pair of binoculars I have there is like 10 pounds or so. So you need a counterweight to balance that out. But now you're stepping away from the center of the tripod. So now I can move with a lot more freedom to look up and down, left and right.
45.
Okay, sorry. I'll go real quick. They got 3 more pages here. So these ones are German equatorial mounts. This is the other directional system, the coordinate system you can use. Instead of up, down, left, and right, you're looking at Polaris and saying, how far around Polaris do I need to rotate? And then how far away from Polaris do I need to go to get to the target I'm looking at? This is largely used in photography, but you'll see it quite often, like the one on the left, even for your visual scope. And this one has those same kind of, minutia knobs, so you can adjust fine tuning. But it's just a different way of figuring out, okay, if I want to get to Jupiter, now I can't just move left, right, up, down. I have to go pivot so that now my second axis is in line with Jupiter and then move away from Polaris. It also requires you to polar align ahead of time, which means we first set the scope, making sure that that primary axis is facing directly at Polaris at the right angle so that it can move around Polaris accurately. So those are the axes that's rotating on. You can get a wedge mount for an alt-az mount that will basically convert the alt-az into a equatorial style system. So in this one, now you've got this. So instead of just pivoting on a horizontal plane, you're pivoting while you're pointed towards Polaris. So that's that rotation around Polaris. And then this would be moving away from Polaris. Push to and go to, you'll see commonly. Push to is this. Go to is the same as push to, except for go to has motors. So push to has sensors. So as you move the scope, you can see how far away you are from the target you tell it you want to go to, but you manually push it there. And it will tell you like you're 34 degrees to the right and 12 degrees to the lower. So you're low of the target. So as you move it, that'll count down to 0, and that helps you hone in on it. Whereas the go to, you can tell it once you're aligned, I want to go to this target, and it does all the motion for you. Trackers is really, that's a type of mount. You may run across them. It's an astrophotography only thing, so you can pretty much avoid that. But basically, they only rotate on one axis. They'll rotate around Polaris, but they don't do the other position automatically in any way for you. Real quick, this is that polar alignment thing I was talking about. I know. So yes, so
this is beginning.
I know. Just real quick, so you can see that this is, you're rotating around and then you're moving away, right? So that's how you're dialing into that. So it's different than just going up, down, left, right. You're actually pivoting around and going away. So those are the equatorial versus alt-az. Those are the kind of mounts you're going to be looking at. So that's it.
Okay. Problem with astronomy is there's so darn much of it.
I know.